Hello, we'll start a second lecture, pointers to 2D arrays. We have just learned pointers to 1D array. So if P is a pointer to a 1D array, then you can access the elements of a 1D array by writing star of P plus I. So therefore, how do you manipulate what you have learned for 1D arrays to make a pointer P access the elements of a two-dimensional array? So well, how do you manipulate what you will learn for a 1D array to start accessing the elements of a 2D array? So again, let's consider the same step. If P is a pointer to a two-dimensional array, then how do you write elements of a P? So therefore, if P is a pointer, then you declare pointer by writing in star P. P should be initialized if a two-dimensional array A of 3 by 3, then P should be initialized with the base address of the array. Base address of the array is nothing but the address of the first element. So therefore, it should be initialized with A of 0, 0 here, or in other words, it can also be initialized with ampersand A of 0, where A of 0 is the address of the first row, or it can also be initialized with the base address of the array P is equal to A, because array name itself stores the base address of the array. So therefore, you can use any of the notation, either P is equal to A of 0, 0, or P is equal to ampersand A of 0, or P is equal to A. So for our convenience, let us limit our discussion by using P is equal to ampersand A of 0, 0. So therefore, how do you access the elements of a two-dimensional array? So imagine, we all know that the two-dimensional array elements are stored row-wise contiguous. So therefore, if there is an array A of, then the elements are in the locations row-wise consecutive. So therefore, there are 9 elements, row 1, row 2 and row 3, each row having 3 elements. So they are stored row-wise contiguous. This is row 1, row 2 and row 3. So the indices are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1 and 1, 2, 2, 0, 2, 1 and 2, 2. So again, if the base address is 100, the next element is at 102, next element is at 104, next is 106, 108, 110, 112, 114 and 116. So this is how the elements are stored. Assuming that the elements are 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8 and 9. The in line 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let us see what is the, so we know that if P is a pointer, imagine if P is equal to ampersand A of 0, 0, then we access by writing P plus I plus J, isn't it? Just like how we did it for 1D array. So let us check what is the address if we are trying to access A of 0, 1. A of 0, 1 is equal to 100 plus 0 plus 1, which is nothing but 100 plus 1 into 2, nothing but the scaling factor, which is 102. Yes, the address of A of 0, 1 is obviously 102. So this is okay. Now let us take the second one. Let us check the base address of A of 10. A of 10 is the first element of second row. Obviously the address is 106. So let us see what do we get. A of 10 is nothing but 100 plus 1 plus 0, which is again 100 plus 1 into 2, which is again 102. In all these cases, we get the same answer for A of 10 and A of 01, A of 02 and A of 20, A of 23 and A of 32, because we are always doing I plus J. So therefore, the point to be noted here is, in order to access the elements of a two-dimensional array using its pointer P, it is not simply P plus I plus J. There is something which is missing. What is that which is missing? The only thing that we need to understand is, whenever a row jumps from one row to another row, it needs to jump column number of elements. So if a row has 3 elements, 1, 2, 3, if a row has 3 elements, whenever you jump from row 1 to row 2, it needs to jump 3 elements. So implies to jump from one row, a row requires column number of elements to jump to. So in other words, the answer would be ideally It's not P plus I plus J. Instead, it is, if P is a pointer to a two-dimensional array, then it is P plus I into C plus J, which gives you what is called as ampersand A of Ij. So ampersand A of Ij is nothing but P plus I into C. Why I into C? If you do not write I into C, implies the row jumps only one element and you don't have the scaling factor. So this is the needed scaling factor that helps you to ideally identify the correct element in the current row. So let us take up an example directly and try to see how does this work. Okay, so therefore, what do you write? So we finally conclude by writing, if P is a pointer to a two-dimensional array, if P is a pointer to a two-dimensional array, then ampersand A of Ij is equal to P plus I into C plus J, and A of Ij is equal to P plus I into C plus J, but only thing, it will have a star before, because A of Ij talks about value and ampersand A of Ij talks about address. So pointer essentially holds address, and if you want to get to the value at that particular address, you have to have an indirection operator before the address. So indirection operator directly helps us to get to that particular address and read the value from there. So if P is a pointer to a two-dimensional array, then star of A plus star of ampersand A of Ij is equal to P plus I into C plus J, where C is the column size. C is column size. And A of Ij is equal to star of P plus I into C plus J. So let's take up an example and try to study how does pointers to 2D array work. So Alt F, let's move and open this program. PTR to 2D. So this is a program that, so I have an array A, a two-dimensional array of 3 elements. In star P, I have initialized it to the base address of the array, which is A of 0, 0. So then you read the elements. We already learned ampersand A of Ij is nothing but P plus I into C plus J. So what is the column size? Column size here I ideally kept it to be 3. So therefore it is P plus I into 3 plus J. And the value is obviously star of P plus I into 3 plus J. So let's run the program, compile and run. My dear boys and girls, in all the cases where I wrote star of P plus I into C plus J or P plus I into C plus J, you can always replace P with A, because array name itself stores the base address. Both works. So I'm asking to enter values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, this is a 3 by 3 array which stores 9 elements. So therefore the indices are A of 0, 0, 0, 1, 1, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1 and 2, 2. Check out the addresses. It is pretty clearly seen. It is at 6, 8, 10, 12, 14, 16, 18, 20 and 22. This is also enough to show that array elements are stored row-wise contiguous if it is a two-dimensional array, and all the elements are stored in adjacent or contiguous memory locations. So therefore, in all the places where you have to write ampersand A of Ij, you should be end up writing, if it is a pointer, writing star of P plus I into C plus J. And in all the places where you want to write ampersand A of Ij, you have to write star of P plus I into C plus J, where you can replace always P with A. P can always be replaced with A. So this is how you tend to access your elements with 2D arrays. Access the elements of a 2D array using its pointer. So likewise, if you are writing a matrix program where you are trying to add your elements, then the easiest way of doing this is, in any place where you have A of Ij, replace it with, simply just replace it with star of A plus I into C plus J. And in any case where you have B of Ij, replace it with star of B plus I into C2 plus J and C1 plus J, where C1 is the column size of first matrix A columns of A and C2 is columns of B. If it is matrix addition, C1 is equal to C2, but if it is matrix multiplication, C1 and C2 are different. May be different. So therefore keep that note and you can write any program of a two-dimensional array using its pointer, not a big deal. So hope you're okay with it. I wish you to try a few more programs using pointers for 2D arrays. On that note, thank you.